Welcome everybody. Today we will start explaining Maxwell equations, and we will move by step until we reach how to get the equations of the wave moving in a rectangular waveguide. The four Maxwell equations are known: div E equal rho over epsilon naught. Rho is the free charge density. Div H equals 0. Curl E is equal to negative the permeability multiplied by the partial derivative of h with respect to time. Curl h is equal to permittivity multiplied by partial derivative of E with respect to time plus J, the current moving in the medium. Of course, all these equations are vector equations. We will assume that we are using the coordinates x, y, z. If we are going to study the rectangular waveguide, we will assume that it is a source-free medium. I mean by this that we are far from the source and far from the load. We are working in the middle. So rho will be equal to 0. And J will be also be equal to 0. We will also assume that the wave is a time harmonic, which means it's a function in time in the shape of e to the power of j omega t. So any derivative with respect to time will be j omega. So we can remove these two derivatives and replace them by j omega. If we assume that the wave propagates in positive z direction, then we can write it in this shape. Any derivative with respect to z will be negative lambda. Lambda is equal to alpha plus beta j. For now, we will assume that this is a lossless medium, so alpha is equal to 0. Therefore, lambda is equal to beta j. So any derivative with respect to z will give us negative beta j. Mathematics revision. If A is a vector that has components in the x, y, z direction, then curl A can be calculated from this determinant, and the result will be also a vector. If we apply this rule on equations 3 and 4 of Maxwell, we can return to them. We'll apply this rule to the last two equations of Maxwell. We'll get these expressions. These expressions are written using E small, not E capital. The difference is that E capital is a function in x, y, z, but since we already know the function, its relation to the z, we removed it and we only use E small just to make mathematics a little bit easier, and any differentiation with respect to z, we will use negative beta j. These two equations are vector equations. Each one of them can give us three scalar equations, so we can reach those 6 equations. Those 6 equations connect between the transversal and longitudinal components of the electric and magnetic fields in the medium. What we'll do in the next slide, we will get the longitudinal components, Ex and Ey, Hx and Hy, in terms of the transverse components. We'll get the transverse components, Ex, Ey, and Hx, Hy, in terms of the longitudinal components, Ez and Hz. If we substitute equation 5 into equation 1 by removing Hy and replacing it by this expression, and by a little bit of mathematics, we can reach this expression. Notice that Ex is a function in Ez and Hz. Each one is a derivative in a different direction. This is Ez is differentiated with respect to x. Hz is differentiated with respect to y. Notice the term omega squared u epsilon minus beta squared. This term is very important and we will refer back to it later. If we do the same thing by replacing equation 4 into equation 2 by removing hx and replacing it with the expression, we can get ey using the same mathematics steps. We can reach this expression. Notice that's also function Ez Hz, but this time the derivatives are switched. The denominator still is the same, omega squared u epsilon minus beta squared. Hx, we can bring it by substituting equation 2 into equation 4. We remove the ey and replace it with this expression. Hy, same method, substitute equation 1 into equation 5. Notice that we didn't use equation 3 and equation 6 because we want the transverse components with respect to the longitudinal components, not the opposite. Now we have 4 equations for the 4 longitudinal components. We said that all of them share the same denominator, so the denominator must have an importance. The denominator is called, we will refer to it as Kc squared, where Kc is called the cutoff wave number. Omega squared mu epsilon is called the wave number. So basically, Kc squared is equal to K squared minus beta squared. By just bringing the beta to the left hand side of the equation and Kc squared to the right hand side of the equation, we get, and taking the square root of both sides, we get an expression for beta. Notice that there are 2 solutions for this equation. Inside the square root, the result could be negative, positive, or 0. Let's study if the expression inside the square root is negative. A negative number inside the square root gives us an imaginary number. So beta will be, for example, positive negative xj. If we get lambda, which is beta j, we get alpha plus minus, or minus plus, j times j gives us negative x. We will refuse the negative sign because this means that the wave gains power as it propagates through the medium, which is wrong. Wave loses power. So we will see that alpha is equal to alpha plus x, which is a real number. This means that the wave is attenuated very high and it dies fast. For beta to be a real number, k squared must be greater than kc squared, which means omega square root mu epsilon must be greater than kc. The middle point is the cutoff point, where k is equal to kc. If we remove square root epsilon mu epsilon, if we work in the free media in air, we can assume that the square root epsilon times mu is equal to 1 over c, and we remove omega to be 2 pi f. Then at the cutoff point, 2 pi cutoff frequency over c is equal to kc. So now we can get an expression to the cutoff frequency, which is equal to speed of light over 2 pi times kc. What is kc? We don't know until now. Modes in waveguide. The waveguide can have 3 modes: TEM, TM, and TE. We'll study them one by one. First of all, TEM stands for transverse electromagnetic wave, which means that EZ and HZ are both equal to 0.